And so that green area, we're working at the moment with the developer to look at a solution where we can incorporate our facilities into his development plans. And then we're going to move on now to minimising financial risk. There's a very large component here which we are fairly passionate about. Like I say, it's the ability to phase to reduce financial risk. What do I mean by phasing? Well, I said that at the end of a 20-year projected build-out, so this isn't existing flow, this is what's projected, we would be seeing around about 180,000 gallons per day that we need to accommodate. What if that doesn't happen? What if we built a 180,000 gallon per day treatment plant on day one, but we only see 50,000 gallons per day of development? Well, that entire system and the model behind it was based on the fact we were going to be taking in user rates to recover that capital. All of a sudden we have a shortfall in revenue. What happens? One of three things. Either we need to increase the district to bring in more users, we need to increase user rates, or we need to subsidise from the tax base. Another way of doing this is breaking down that 180,000 into smaller incremental installations, 30, 50,000 gallons per day, building it up every 5 years, reacting to growth, reducing the short-term carrying capacity of the infrastructure, and minimising the risk. The problem with this is, at small scale, these technologies can become less affordable. So we need to know that we're working with the right technology, which is what I'll talk about in a moment. But just to show you here, roughly speaking, what a phasing approach might be able to do. Well, conventional phasing to meet the full build-out, 182,000 gallons per day, we'll be talking about a capital cost up front of about 18 million. If we did this in 5 phases, we'd be reducing the maximum phase to about 61,000 gallons per day. We'd also be reducing the one-time capital cost in today's money terms to about 6.8 million. So this is far less geared risk, especially if we're dealing with anything more than a public financing model. The overall amount we pay at the end of it in today's money terms, 21.9 million, is more expensive than doing it all at once. But we've just absorbed this capital in a different way and reduced the risk. And what about the opportunities to actually transfer that risk entirely? Okay, we've looked at a way of minimising it, but what about if the user base, the tax base, had no risk whatsoever? Well, for that to occur, we'd need to shift ownership. We wouldn't be talking about a public ownership model, we'd be talking about a private ownership model. And this risk allocation table just basically breaks down all the different facets of risk that wastewater utility projects are going to inherit. We're talking about design build risk, asset management risk, finance risk. Under public conventional ownership, all this is with the town. But if you did it in a situation where there was private ownership, all this gets shifted to the private entity. Now, what's the advantage here? It means that all of that risk is now completely removed from the tax base. There's no way the tax base can be held accountable. The only people that would respond to any risk through the private entity would be those who contractually are served by the private entity, i.e. the users of the system. But how does it work in Massachusetts? At the moment, there really aren't any private for-profit utilities. There are numerous private non-profits, such as homeowner associations. And it's not that they aren't permitted, it's just that the regulations behind them, which are stipulated by DEP, just don't make it very clear about how to implement this in a for-profit facet. But it's very possible. And one part is here is that it's not regulated in the same way as other utilities, which means that you can be very innovative about what solutions you approach to make things work, i.e. phasing in combined energy and water solutions, novel finance recovery mechanisms. Another way of doing it is through a public-private partnership. So here we actually see a shift of some risk. Maybe the town retains ownership, but the private entity assumes all the financial and performance risk. That's another way of shifting the vast majority of risk, which could have a significant impact to the tax base. The one thing with this is, it would require special state legislation. You know, at the moment in Massachusetts, the way this is set up, it's not possible for a municipality to procure a full DBO, the design, build, operate. Instead, if they wanted to do that, they'd have to pass it first through special state legislation, but it's absolutely possible. And what would we be talking about becoming here if it was going to be some kind of private utility model? Well, you're going to hear this expression quite a few times in the remainder of this presentation. and that is the Responsible Management Entity, the RME. And it reminds me a little bit of the diagram that Nick showed in his presentation, where he had users, he had the institutions or the organizations, and then he also had at the bottom everything else, which is, you know, the actual entities. And I just thought that perhaps the RME would sit quite nicely in the middle of those 3 points in terms of being able to link them all together. And the way that that manifests itself, the P3 or a complete private arrangement, may vary from situation to situation. So it might be a design-build system, it might be a design-build-own-operate, maybe it's just design-build-own, you can have design-build-own finance. What I'm saying to you is that there are numerous ways which the private sector can help to implement projects through novel financing mechanisms which haven't really been exploited properly in the past in the wastewater sector. Now, I'm just going to give you one example here from Massachusetts. This is something that you should all know pretty wholeheartedly, Foxborough Gillette Stadium. This was back in 2005 when the stadium installed a membrane bioreactor to do on-site reuse toilet flushing. Now, if you look into the details of this, it was actually procured on a 20-year DBO. Now, of course, this is a private entity, so they didn't need special state legislation. But it's an example of a working model in place. And it's also an example of one whereby we have multiple users who are benefited by this system. The actual availability of the system enabled some economic stimulus around the stadium, the growth of amenities, and all of those became clients for the system, which is ultimately coordinated by Gillette Stadium. But there are multiple people who have a buy-in for this system. Okay, so moving on to appropriate technology. I'm not going to dwell too much on this, apart from saying how it worked for Littleton. What we know about technologies at the moment, especially at the small scale, is fairly cutting edge because we have good experience across a portfolio of operations and design for small scale activated sludge, MBRs, SBRs, constructed wetlands. We have these systems in our inventory. We've either designed them, built them, operated them, or some combination of the three. Some of them we own as well. So what we know is that when we're really down at a small modular scale, up to about 100,000 gallons per day, if we're talking about secondary treatment and then dispersal afterwards, we can do this most affordably with treatment wetlands. If we're moving much above that in terms of module size, different technologies become more affordable. And this is just important for us as an RME to ensure that we are actually investing in the most appropriate technology solution for our particular problem. If we look at it in terms of a life cycle cost scenario though, so we factor in the operating costs for the system as well, then that goalpost shifts. We're now down at around about 60,000 gallons per day, which is the sweet point beyond which it becomes less affordable to use a constructed wetland system. But as you probably saw at the start, in terms of the phases we were talking about for Littleton, somewhere between 30,000 and 60,000 gallons per day, we knew that the best approach here was probably going to be the wetlands, at least economically. We just needed to make sure that it fit in with everything else. And one of the things that you probably saw in the list of parameters that was given back by the survey from Littleton was that this system is not an unsightly eyesore, does not emit odours, and emits no loud noise. It was the fourth most important point out of 20 that we received back. Now, I'm not slamming ASP technologies. There are some which are subsurface, like the Advantex, they can sit in the ground, and they are very benign. You wouldn't notice them environmentally. But there are great opportunities with wetlands, which we know of, to do things which are a little bit special. Now, I've got one picture here of a very recent system that was built on the West Coast. This is an indoor reuse system. And so it has to be hot from aesthetics and odor control, because otherwise it would be a nightmare. And this is a great system. It's not by us, it's by World Water. And they actually do reuse from this for toilet flushing, cooling, irrigation. It's a real win. I've had some other pictures out to take them out for time, but there is also great opportunities for landscape architecture integration, aesthetic benefits and amenities which can be brought through the right system. So if you're doing a green first approach and you want this to work, then this could be a good option, and we knew this for Littleton. Now, I put this slide in for the case of the Cape in particular, because I know that we're so concerned about nitrogen here. Now, a lot of people say, once I start talking about wetlands, that these systems aren't capable of achieving the limits of nitrogen reduction which we're talking about. So this is the same system that we just saw a picture of the Port of Portland building on the west coast, you see that because of the way they have water conserving fixtures coming in here, they actually have very concentrated nitrogen coming into the system. It's around about 150 milligrams per litre at ambient operation. For those of you who know wastewater, that's probably twice as much as we typically get in the worst case scenarios in conventional systems. But they're reducing the total nitrogen on this system to around about 3 milligrams per litre. Under 1 milligram per litre of ammonia, the rest of it is the TKM. And so in terms of the ability of wetland technology or natural systems to achieve the strict treatment requirements that you're looking for nutrient removal, that's not in question. We're beyond that. Technologically, the scientific community's moved beyond that. The question now is about affordability and making sure it's the right fit.